Welcome back to lesson 3. We introduce Markov chains. Let EJ and EK be two events. Then the probability EJ, EK is the same as the probability, the conditional probability of event K given event J multiplied by the probability of event J. This can be seen from the Bayes theorem. This is the same as the probability of event J multiplied by, if we make rearrangements, K given J. And this can be labeled as AJ PJK, where AJ is equals to probability of event J and PJK is the probability, the conditional probability of event K given that event J has occurred. Extending this to 3 events, the notation to 3 events, say event J, event K, and event R, we have probability of event J, event K, and event R is the same as the conditional probability of event K, event R, given event J has occurred, multiplied by the probability of event J. This can be expressed as the probability, the conditional probability of event R, given that event K has occurred, multiplied by probability of event K occurring, given that event J has occurred, multiplied by the probability of event J. And this is equivalent to AJ, using previous notations, AJ, then PJK, PKR. Definition. A sequence of trials with the probability or with possible outcomes EJ naught, EJ1, EJ2, all the way to EJ n-1 and EJN is called a Markov chain. If the probability of event J naught, EJ1, event J1, all the way to event Jn-1, event Jn, is equals to EJ naught, P J1, J1, then P J1, J2, and this continues all the way to P Jn-1, P Jn. If this holds, then we call such a Markov chain where AJ naught is equals to the probability of event J naught is called the probability at the initial or 0th trial, and Pjk is the fixed conditional probability of event K given event J. We define some terms here. So let's look at some terminologies we are going to be using here. The event EJ will be called state EJ. So EJ here will mean a state. The conditional probability Pjk will be called transition probability from state J to state K. And Pjk, which is probability of event K given event J, will be equals to the probability of moving from state J to state K. Or we can write the probability of moving from state EJ to state EK. We can express transition probabilities transition probabilities in matrix form as follows. Consider states 1, state 2, state 3, state 4, and so on. Then consider on this side we have state 1 again, state 2, state 3, state 4, and so on. Call this the matrix P. Now, the matrix P consists of probabilities P11, P12, P13, P14, and so on. Then we have here P21, P22, P23, P24, and so on. Then we have P31, P32, P34, P33, P34, and so on. And then we have P41, P42, P43, P44, and so on. And this would continue then up to some point. This is called the transition matrix. It can either be finite or infinite. This specifically, if we pick some points on the transition matrix, say the point P11, that transition probability here. It is the probability of moving from state 1 to state 1. If I pick this, then it is the probability of moving from state 1 to state 2 in one step. So this will represent probabilities of moving from one state to another given a number of steps. So the transition matrix can either be finite or infinite. And strictly, if you sum all probabilities in a transition matrix, you should get 1. And this has to be greater than or equal to 0. Any probability is in the matrix cannot be less than 0. And when you sum them, you should get all the probabilities, you should get 1. Now, any matrix whose elements P, J, K are greater than or equal to 0, and if you sum those probabilities, you get 1, is called a stochastic matrix. Examples: this is a stochastic matrix, because if you sum 0 plus 1 plus 0 is 1, 0 plus 1 is 1, and this is greater than 0 and this is equal to 0, so it qualifies. Another example, we have the matrix a half, 0, a half, then we have 0, a half, a half, and then we have a half, 0, a half. We also have another form here. We have example number C. We have a third, 0 to third, 0, a third, to third, and we have a third, 0 to third. All these are stochastic matrices, and strictly we will concentrate on the rows in this case. So if the rows add up to 1, like in this case, then it's a stochastic matrices. You notice that the columns do not add up to 1. So if there is a situation where both the rows and the columns add up to 1, then we call that a double stochastic matrix. But just if only the rows add up to 1, then we have a stochastic matrix. So if each column adds up to unity, that is 1, then we have a double stochastic matrix. E.g. here we have 1, 0, 0, 1 and a half, 0, a half, 0, a half, and a half, 0. You notice that in this case, both the rows and the columns add up to 1. That's why we are calling it a double stochastic matrix. Now let's look at higher order transition probabilities. Higher order transition probabilities. Now let P, J, K, N be the probability of moving from state j to state k. In n steps. In particular, pjk2 is the movement from state j to state k in 2 steps. That is, pjk2 is the same as summation of lambda, then probability of moving from state j to state lambda, then to state k. In general, pjk with n steps is the same as summation over all lambda pj lambda n minus 1, then p lambda k, provided you started from j, went to lambda, given a number of steps n minus 1, then when at lambda you went to k in a single step, then this should hold. In the matrix form, we have that p raised to power n is equals to p matrix n minus 1p, and p matrix raised to power m plus n is equals to pm matrix multiplied by p matrix n. These equations are called Chapman-Kolmogorov equations. Since p jk raised to power n should be greater than or equal to 0, it is not always possible to move from state to state. Let's consider an example here. Consider the transition matrix E1, E2, E3. We have E1, E2, and E3. We have 1, 0, 0, 0, a half, a half. Then we have the third, 0, 2, third. This is a stochastic matrix, but it's not a double stochastic matrix because we have the columns. The columns not adding up to 1, but the rows are adding up to 1. Now the state K is said to be reachable or accessible from J if there exists some positive integer n such that p jkn is greater than 0. So if it's greater than 0, then it implies that you can reach state k from state j. So if it's 0, it means you can't reach. So for n is equals to 0, we have that pjj 0 is equals to 1. Like p11 in our case was 1. Then pjk 0 is equals to 0 for j not equals to k. Now if the movement from state j to j is possible, and movement from state j to k is also possible, then it implies that movement from state, let's consider this to be state I. So movement from state I to state j and movement from state j to state k is possible. Then it means that you can also move from state I to state k. We started with I, went to j, from j we went to k. So it means that we can move from state I to state k. And there exists some positive integer m and n such that pijm is greater than 0 and pjkn is also greater than 0. Using Chapman-Kolmogorov equation, we have pik m plus n is equals to the summation of our lambda pij m pjkn is greater than pij m pjkn, which is greater than 0. And therefore, pm plus n ik is greater than 0, implying that state k is reachable from state I. Look at the relationship between Pij n and Fijn. Pjkn is the probability of moving from state J to state K in n steps. And this is regardless of the number of steps, or regardless of the number of entrances into state K prior to n. We define Fjkn to be the probability of entering state K from state J in n steps for the first time. In PJKN, we are not considering the number of steps you've been to K when you started at J. But for FK, we are saying it's the first time you got to state K, given that you started from state J. Now, we can find the relationship between PJKN and FJKN, then use them to find PJJN and FJJN. Let the first return to state J take R steps. In this case, the probability will be FJJR. The probability of the remaining n minus r steps will be PJJN minus r. Therefore, PJJN is equals to summation r starting from 0 to n, FJJR, then PJJN minus r, n greater than or equal to 1. You can label this 1. So that if this is the first time I'm entering state J from J, then the remaining will be n minus r, probability of J of entering state J from J in n minus 1 steps, because we already used r steps, given that r is smaller than n in that case. From this, we have, in terms of generating functions, define PS to be equals to summation lambda is equals to 0 to infinity, PJJ lambda, then s raised to power lambda, and capital F of S to be equals to summation U starting from 0 to infinity of FJJ U s raised to power U. From 1, we have summation n is equals to 1 to infinity of PJJNSN is equals to the double summation, because we are splitting the interval. N is equals to 1 to infinity, R is equals to 0 to infinity of FJJR PJJN minus R, then S raised to power N. This can further be written as PS minus PJJ0 is equals to double sum N1 R0 both to infinity. Then f j j r s r, then p j j n minus r s n minus r. This is equals to r is equals to 0 to infinity. Take it each summation at a time. J in r steps, s raised to power r, then summation n minus r to infinity, p j j n minus r s n minus r. This is the same as ps minus 1 is equals to fs, considering the definition for fs and ps. So that we have, therefore, ps, making ps the subject of the formula, we're going to have 1 over 1 minus f of s, which is the relationship between p and s. Let's now look at classification of states. One, persistent state. A state, EJ, is said to be persistent or recurrent if capital JJ is equals to summation over all n small jjn, which is equals to 1. Number 2, transient state. A state EJ is said to be transient or non-recurrent if fjj is equals to summation n fjj in n steps is less than 1. So if it is equals to 1, then it's persistent. If this summation is less than 1, then it's transient or non-recurrent. If fjj capital is equals to 1, then f small jj is the probability known as the recurrent time distribution. In general, if fjk is equals to summation over n fjk n is equals to 1, then fjk is the probability called first passage distribution. The mean recurrent time for state J is given by mu J is equals to summation over n n f j j n. If mu j is equals to infinity, then state j is null. If mu j is less than infinity, then state j is non-null. Theorem 1. If state j is persistent if and only if the summation over all n of pjjn is equals to infinity. But we should note that the limit as n tends to infinity of pjjn is equals to 0 for some null state. Theorem 2. State j is transient if and only if summation over all n of pjjn is less than infinity. Classification number 3, periodicity. A state is said to be a periodic T if T is the greatest common divisor of n such that pjjn is greater than 0. If t is equals to 1, then the state is said to be a periodic. Definition number 4, ergodicity. A state that is persistent non-null and aperiodic is said to be ergodic. Number 5, absorbing state. A state is absorbing if once entered, it cannot be left. That is, if pkk is equals to 1, then k is ergodic, e.g., consider state 1, state 2, state 1, state 2, matrix. You have 1, 0, and a half, a half. Now, P11, the probability moving state from state 1 to state 1 is 1. From the matrix, E11 is 1. And therefore, this means that the implication here is that E1 is an absorbing state. Another definition, a closed set. Number 6, closed set. A set C is said to be closed if no state outside C can be reached from any state in C. Thus, if EJ is a member of C and EK is not a member of C, then PJK has to be 0, implying that however number of steps you carry out, you will never reach K from J. Now, if state J, state K are members of C, then summation over all K, Pjk should be equals to 1, implying that summation over all K of Pjk in n steps is 1 for n is equals to 1. We have an irreducible Markov chain. A Markov chain is irreducible if there exists no closed subsets. No closed subset other than the set of all states. Look at an example. To classify the states of the following transition probability matrix. So the matrix we need to classify is the matrix P such that it has states 1, 2, and 3. With probability 0, a half, a half, a half, 0, a half, then a half, 0. So we notice that this is a double stochastic matrix. So for the solution, we first draw a tree diagram for our case. Now, if we're starting from state 1, we can move to state 3, or we can move to state 2. When we are at state 2, it is possible to move back to state 1 or go to state 3. When at state 3, it is possible to move to state 1 and we can go back to state 2. And now the process then repeats itself. And if you look, we have been able to consider each of the states in this diagram, and therefore it means that we can reach all states starting from the first state, including the first state itself. So this means all states are reachable from one another. So that we can say that the chain is irreducible. Now, since the chain is irreducible, all states have the same property. Therefore, we can use one state as a representation of all the others. We shall consider only one state to be a representation of the others. Say the first state. Now, F11 in 2 steps, to move the probability of getting from state 1 to state 1 in exactly 2 steps. The first time means the probability of moving from state 1, go to state 2, then go back to state 1. Or probability of moving from state 1, going to state 3, then going back to state 1 again. You notice that this is the probability, this is with probability a half multiplied by a half. That is, moving from state 1 to state 1 has probability a half. Moving from state 2 to state 1 has probability a half. Then plus a half plus a half times a half for the second part. And this gives us a half. Now, the probability of moving from state 1 to state 1 in 3 steps exactly will be probability of moving state 1 to state 2 to state 3, then going back to 1. Or probability of moving from state 1, going to state 3, back to state 2, then we go to state 1. And this is with the probability a half, a half, a half, plus a half, a half, a half, which is actually a half squared. Now, if we are looking at F1, probability of moving from state 1 to state 1, in the first time in 4 steps, then this will become a half cubed, and that will continue, so that probability of moving from state 1 to state 1 in n steps is then a half raised to power n minus 1. This was 4, so 3. So when we have n, then this will be n minus 1. So capital F11, which we defined as the summation of all n of 1, 1, n, is equals to summation n starting from 2. We don't want to start from 1, so that doesn't become 0 here. Then to infinity of a half n minus 1, which is actually equals to a half plus a half squared plus a half cubed plus all the way to infinity. If I replace with 2, the first time becomes a half, 3 becomes squared, 4 becomes cubed. So this is a converging geometric series, and therefore we can use sum to infinity is the first term, divide by 1 minus the common ratio r. So that in our case here we are going to have a half, divide by 1 minus a half, which is 1. And therefore, this implies that E1 is persistent. Then define U1 to be equals to summation over n f11n, which is the same as summation n is equals to 2 to infinity of n a half raised to power n minus 1. I've replaced f and n. This is the same as 2 raised to power half plus 3 raised to power half squared plus 4 raised to power half cubed plus all the way to infinity. Now this is the same as 1 plus 2 a half plus 3 a half squared plus 4 a half cubed plus all the way to infinity. But because I've introduced 1 here, I need to subtract it out here so that it remains this way. Now with that, let's consider this. F prime is equals to 1 plus 2x plus 3x squared plus 4x cubed, and so on. Now, considering this expression, let's look at an expression of f of x as x plus 2x plus x cubed plus x power 4 plus all the way to plus c. Now, if I differentiate this function, the second function, I get the first function. The derivative of x is 1. The derivative of 2, the derivative of, rather, this is x squared. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. So it means that if I differentiate this, I get the first part. And we can use that property and see that if x is, absolute value of x is less than 1 strictly, then we have that u1 will be equals to x all over 1 minus x plus c. Using the same transformation and going back to what we had, we have that therefore f prime of x must be equals to 1, if we differentiate this with respect to x, is 1 multiplied by 1 minus x using the quotient rule, minus x multiplied by negative 1 divided by 1 minus x squared, which is 1 over 1 minus x squared. And therefore, u1 is equals to 1 all over 1 minus a half x squared minus 1, which is equals to 4 minus 1, which is equals to 3. And we notice that this is less than infinity, which implies that E1 is non-null. Let's look at P112. This is P, E1 to E2 to E1 again, plus P, E1 to E3 to E1 again, which is actually a half. We've seen that this is becoming a half. If we do P3, 113, this is P, E1 to E2 to E3 back to E1 plus probability of E1 to E3 to state 2, then back to state 1. And this is equivalent to a half squared. We've shown that. Now, if that continues, then we are going to have the highest common factor of these powers, 2, 3, and so on. 2, 3 is 1. These numbers have only 1 as the common divisor. That implies that E, or event state 1, is a periodic. Therefore, we conclude that E1 is persistent, non-null, and aperiodic. Thus, E1 is an ergodic state. Hence, the chain is irreducible and an ergodic Markov chain. That's the end of lesson 3.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.